your material, even if it's supposed to be exactly the same day to day, coming from the vendor, will never be exactly the same. In fact, you buy it with a specific range in terms of properties, and the vendor guarantees that it stays within these properties, and if it doesn't, you reject it and you get new material and so on. So the raw material in and of itself has some variability because the microstructure is not consistent enough to give you the exact same stiffness, let's say, and the exact same strength. Manufacturing, especially if it's based on humans manufacturing, it involves all kinds of human error in terms of the sizes of the parts and how they are located, the orientation of the fibers. So that introduces error, and there are all kinds of other factors. Even if you were doing it with robots, you still have some variability. So that means you have a scatter in your specific properties, which will include this raw material variability. But it's also sensitive to, there's also one over there if you want. It's also sensitive to environmental effects, especially composites are much more sensitive to higher or lower temperatures than room temperature and the amount of humidity it's been absorbed. And of course, what kills everything, or what makes composites not the winner in every case, is the effect of damage. Any kind of damage that in a metal at most would be a little dent with localized yielded structure in a composite could reduce the strength by as much as 50%. So if you take all these, if you take material scatter, alone first, then, for example, this is typical tension strength data. And this is the strength in megapascal shown on the x-axis. Then the distribution of the tension strength is here. And for the exact same material, the distribution of the compression strength is here. Typically, compression is slightly less or significantly less than the tension. Obviously, you cannot take the average value, because if you take the average value, then there's a whole bunch of material that would be coming in with strength lower than the average that you could be using, and you had assumed the average value, and obviously you are being unconservative. So there are two values that are statistically defined, the so-called B basis and A basis. And those are the values we use for design. And they are, in fact, dictated in the design process by both the certifying agencies, but also the manufacturers of the design. The B basis is the 10th percentile. Basically, 90% of the tests you would ever do on that material would be higher than that value. And the A basis is the 1 percentile. So 99% of the tests you would ever do would have higher strength. Typically, the A basis is used for single load path primary structure. So if it's a blade and you lose the blade, you lose the aircraft, then that's an A basis design. If it's a skin stiffened structure and it's just a local failure, you can definitely redistribute the load, so it's like a multiple load path or a slightly redundant structure. In those cases, you would use the B basis. And you will be seeing those in your homework. Environment, temperature. Increasing the temperature reduces the properties. So this is the temperature here, this is the cold temperature region, and this is the elevated temperature region. And this typically is the range that you would have to use to design in any flying contraption inside the Earth's atmosphere. If it's in space, then obviously the negative side on temperature is reduced by a lot. I have the tension as a function of temperature, and it's the continuous line, which you will see that around room temperature, then it starts dropping again. And the dashed line with the same color is meant to be the fully saturated by moisture set of properties. So if you actually leave the structure long enough in a very moist environment, you will run into all kinds of trouble because you have an additional knockdown because of the presence of moisture. Similarly, the two sets of curves here are for the compression side. When I was working in a program designing a all composite airplane, the Starship at the time, we actually had to, this was 1980 through 84 through 1990, and it wasn't readily available, like climatic data around the world. So we actually had to contact physically the Meteorological Survey of the United States to give us information for the entire world, and we found that the most humid day in, day out place in the world is the island of Guam, which is actually pretty nice because it's 85% relative humidity. The only problem is that it stays that 360 days a year, you know, unlike Florida, which can get to higher humidity, but there are some days that are drier. And then the hottest place on Earth, without any humidity, is what? Do you guys know? Actually, by name. Yes, very good. Death Valley. It's ridiculous. I mean, on a really bad day, it can get like 100 degrees Celsius even. So the good thing is that it's dry. So if you were designing an airplane that would only be flying in the Death Valley, you would be using the continuous lines, and you would not have to worry about the humidity reduction.
Some of the cure temperature, some of the matrices are about 80 degrees. In that case,
that would be a bad matrix to use then. If your cure, I mean, basically you want to find where your glass transition temperature is, subtract like 10 degrees or so, and make sure your material is going to operate in environments that are at least 10 degrees below that. Or if you want to live with that, but nobody does it to my knowledge, you have to use extra reduction factors for material operating too close to its glass transition temperature. And that's, for a long-term performance in terms of fatigue loading, it's a bad idea because you will really be degrading the structure itself. So, for example, room temperature cure materials, you have to be careful if you intend to use them in very hot environments. So the damage on the other side, anything that you can do to the composite structure will actually affect it. So you can have things like holes drilled on purpose, lightening holes or fastener holes, or by mistake because you dropped some screwdriver, it went through, or some madam dignitary with very spiky spike heels walking through the structure and it's very thin skins. It's happened, and it happens, and you have to design for that. But besides that, you have porosity, basically tiny voids distributed through the structure. You have delaminations, which is bigger voids, that are separation between the layers. And of course, impact. And shown here, the most critical one, this is first generation thermoset composite materials, where the reduction, as you can see, can be down to 60% or more. Newer materials are significantly above this curve, but as a rule, the impact damage tends to be one of the most critical types of damage. So I now have to design my structure, and I have to recognize that even if it's pristine and perfect the day I make it, assuming the people on the shop floor were careful enough, which is not necessarily always the truth, then I have to account for the fact that it will be damaged during service, and I don't want it to be withdrawn from service immediately every time there is damage. And I have two types of requirements. One is damage that I can detect and damage that I cannot detect. Because in composites, even damage that we cannot detect, irrespective of the method you use for detection, causes a significant reduction in strength and to some extent also in stiffness. So if I can detect, we define this parameter, threshold of detectability, and that means that whatever method you chose, it may be able to detect a certain type of damage of a certain size, and if it's smaller than that, it's not reliable enough to detect it. So if you are right at that threshold of detectability, you have to design your structure to take ultimate load, because you have to assume that your structure at some point during its life will actually have that damage in it. And because you cannot see it and repair it, you have to live with it, which means it becomes an ultimate load requirement. Typically, the inspection method or the detection method is based on visible inspection, which is another interesting story. How many people looking at the same thing will arrive at the same conclusion in terms of, oh yeah, I can see the damage there and it's about that size. But that's what we have to live with. So if you choose that the inspection method is visible, then it's barely visible impact damage. So ultimate load for that, and limit load if it's visible damage. So you have to account for both, because sometimes if you design for limit load with visible damage, the knockdown at the limit load is bigger than multiplying that by 1.5 and comparing to your ultimate load. In other times, if you design for ultimate load for barely visible impact damage, then if you reduce by 1.5, you actually are already below limit load, so that is the driver. So you cannot do one of the two and assume you cover the other. You typically have to check for both limit load and ultimate, threshold of detectability, and visible damage. So if I take everything together, I will completely destroy this wonderful material that has these excellent properties. Basically, my strength at room temperature ambient and damaged is somewhere out here. And that's the mean value. Now, I have to reduce this from here to here, 5 to 20%, to account for the worst environmental effects. 5 to 20 depends on the property, depends on the material, depends on the environment you are taking into account. So you're down here, and then you further reduce it to include the worst type of damage. Typically, it's impact damage. And that gives you the mean strength at accounting for environment and accounting for damage. And then around that, we have the distribution. We said the material scatter has a certain distribution, and we'll have to go down here to use either the B basis or the A basis design value. So from here to there, materials which compared to steel would be no contest, would be the best materials in the world, all of a sudden become comparable in some respects. And to translate this to numbers, a typical material has a mean undamaged failure strain in compression of 11,000 microstrain, or 0.011. So if I apply typical knockdowns, these are typical, so don't take them for granted, even though you will see that almost everybody uses these typical, at least for preliminary design. For accounting for environment, we have 80% is the multiplicative factor, or a 20% reduction. Accounting for damage, barely visible impact damage, we multiply by another 0.65, or a 35% reduction. This is for the newer materials, not the first generation thermosets I just showed you, which are not as good as this. And then the material scatter to give us the A or B basis. This assumes a coefficient of variation. This at the bottom left here is meant to say CV, coefficient of variation of 11%, which is a bit on the high side, but it's good to cover most cases. Gives you another multiplicative factor of 0.8, or a 20% reduction. So if you take all these three together and you multiply by this 0.011, you will find 4,576 microstrain. And if you go and look at ever since the 70s, the typical cutoff strain values being used in composites were 4,500 microstrain. So there is a reason which is very much strongly related to this.